In this video, I'm going to briefly go through some of the ways in which we can work with lists in Mathematica. As usual, we start with the Mathematica notebook interface, and we recall the range function, which, if I give it a single argument, gives me a list of integers between 1 and 10. I can find out more about the range function using the query function, the help function. And you can see that I can enter differing numbers of arguments. I can say 1 to 10 to give me the list of numbers from 1 to 10, and I can enter a step size, for example 0.1, to generate a list of values with spacings of 0.1. Notice that there's a difference between this command and this command. You can see that in this command, all the numbers that have been returned have been given as integers, whereas because I have entered in this 0.1 here, all the numbers that have been returned here are floating point numbers. So these numbers will retain the full accuracy of the calculation, whereas these will not. As I said in a previous video, we can correct that by making that step size 1/10, and now I have exact values again, given as fractions. Another function which is very useful to have and to use is the table function, which allows me to generate more complicated things than just a successive list of numbers. So, for example, I can ask for a table of x squared. So let's say x squared for x varies from 1 to 10, something like that. And in this case, the syntax is to enclose the list of arguments or the list of parameters within curly braces. This is quite common in Mathematica. And you can see that I have now generated a table of values. And I can do this for a number of different expressions. I can go back into this and I can now do plus a, where a is some constant, and you'll see that Mathematica not only can do numerical calculations, it can also do algebraic calculations. So if I wish, I can make this to a times x if I like, and it will substitute in, when x is 2, it will substitute, for example, here 2. So this is a very powerful function, the table function. Now, I can also generate lists of lists, which can also be thought of as being matrices. We'll do that manually to begin with. So I'm going to create my first matrix. I'll call this M, and that's going to be equal to a list which is composed of 2 elements, each of which is itself a list. 1, 2, 3, 4. And I hit return, and you can see that the answer is given as the same as the input. I can ask to display this array, or this list M, in a different form by typing matrix form. Oops, should have hit tab there. Matrix form of M, and it displays this matrix in its this list as a matrix. Now notice that M is the list on which we will do operations on. This is the variable we will do operations on, whereas the matrix form of that is merely for display. We can't do operations which are sensible using the matrix form of M. So if I wish to calculate M times M, you can see that it's multiplied each and every element of M with its corresponding element in the other matrix. So this is not a matrix multiplication. Can we do matrix multiplication? Well, perhaps there's a thing called a dot product. There we are. So if we were to do dot of m comma m, as it's suggested in the syntax for the dot function, I now get a matrix multiplication. And if I were to put matrix form around that, whoops, I put matrix form around that, matrix form of that expression, I now see that this is a matrix calculation. Now you will see in the help for the dot function that there is a standard form for the dot function, and as usual it's defined with a capital letter, and there's also a shortened form, which in this case is the dot operator. So I can say m dot m in order to get the same answer. Actually, all functions in Mathematica are like this, and if we go back to the multiply operator up here, we'll see if we do query times to see what that is. Wait a second. Oh, sorry, that won't work because that's going to give us all the functions that are available in Mathematica. So that won't work. Let's try query times. Is that the right function? There we are. It represents the product of terms. So times of m comma m, close brace, is m times n. And in principle I can put as many arguments as I like in that, and it will multiply all those elements together. So this expression is identical to this expression. Now, something I haven't mentioned so far is actually in many situations I don't need to use the times value. The reason for this is that Mathematica is trying to help to display our expressions in a more human readable form. So if I had x times y plus c, you can see that Mathematica has displayed x and y with a small space in between them, which is a little bit like algebraic notation. And actually I can enter exactly that in an expression. So I can say xy plus c, remembering to put a small space, a space in between x and y, and that will be the same as writing x times y plus c. So this expression here and this expression here are equivalent in Mathematica. It's very important, of course, not to type in x, y without a space, because then Mathematica will treat this as a variable called xy. So you have to be careful about that. Something else I can do with Mathematica is I can do what are called postfix operations. So up here I calculated the dot of m and m. So let's do that again. Dot m comma m is the result of multiplying m with itself, doing the dot product, a matrix multiplication. And I can, rather than having this form of applying the matrix form, I can do this instead. I can do backslash backslash matrix, sorry, slash slash matrix form. So this is the equivalent of writing matrix form of something. So this is equivalent to writing this. So any function where I have a single argument, I can replace this way of writing it with this way of writing it, and that can be useful if I want to apply many functions sequentially to a single variable. So, for example, if I define x to be equal to pi, then I can, rather than writing tan of cos of sine of x and then putting lots of brackets around it, I could write that. Or I could write it this way. I could say x slash slash sine slash slash cos slash slash tan, and it will give me the same value. So this slash slash operator, this so-called postfix operator, is very handy in certain circumstances. Now let's go back to our definition of an array up here. So we're going to make x equals range 10. So we'll go to the bottom of our notebook and we'll type x equals range 10. So how do I interrogate one of those elements? Well, the expression for doing that is double brackets. So if I want to find the fourth element of x, it's 4, of course. Let's make that a little bit more obvious. I'll make x equals range 10, and I'm going to add 4z, to that, and you can see that I now have a list of expressions, and I can find, say, the sixth element of that list, which is 6 plus 4z. So as well as being able to do all of this numerically, I can also do it algebraically, which is a very nice feature of Mathematica. If I wish to find the element of m, so I want to find the bottom right element, I would type 2, 2, which would be 4, remembering our original definition of m, which was as so. Oops. Okay. Now, another general feature of Mathematica is that you can define your own functions. So let's define a function which is a little bit different to the square function, and this is going to be a function that squares a value and adds 1 to it. So I can do that using this notation. I can say f of x, and I have to put an underscore there, and I say equals x squared plus 1. And when I type an expression on the right which has some characters which match the arguments on the left, then this sequence here is highlighted to let us know that Mathematica recognizes it as an argument. Okay, so now f of x has been defined. So I can now say, what is f of 2? F of 2 is, oh, what have I done wrong? You can see that I previously defined x up here. So you can see that there can be a conflicting definition if I'm not careful. Remember that a way to get around that is to do evaluation, quit kernel, quit the local kernel, and now I've completely deleted any calculations I've had up to now. So even though those lines are still appearing in my notebook, they have not been evaluated. So I can now click on this line, on this cell, and I can execute it. And now I've defined this function free of any conflicts with any other functions. So please bear that in mind when you're using Mathematica. Now when I do f of 2, you can see that it is giving the correct answer, which is 4 plus 1, which is 5. Now a nice thing that I can do with Mathematica, which I can't do with other languages, is I can substitute anything I like into this. So I can substitute, I can say 3. I can also substitute in z. And it will take z and substitute it in whenever x appears in the expression, and it will give me an answer. If I like, I can put z squared in. It will give me 1 plus z to the 4th. So this is a nice feature of Mathematica that I can again do algebraic calculations. Now a slightly more sophisticated thing that I can do with Mathematica is, rather than having to define a function, I can define an expression and then apply it over many elements. So let's start by looking at this function, and what I can do is I can say, rather than just doing f of a single value, I can say f of, let's do it over 1, 2, 3, 4, 5. And you can see that Mathematica has done its best to take this list of elements and apply them one by one to the function f. For some reason it's hanging up for a moment. Don't worry about that, we'll just continue waiting. It looks like it's going to recover in a minute. So that f has been applied to each and every element of that list that I've supplied. It seems to be playing up a little bit. I'll just abort that calculation. It seems to be complaining. Okay, it seems to be okay now. Now, another way that I can write this is I can use a so-called slot. And a slot is done as follows. I can, using the character hash, which on Macintosh is entered using Alt 3, and on Windows is done with a dedicated key, I can do f of hash, where hash is a slot into which I can slot some numbers. And what I can do now is I can now substitute in using this notation, /dot, and I can enter in those values one at a time, 1, 2, 3, 4, 5. Why hasn't that worked? Ah, I forgot the and. There we are, and map out. There we go. Sorry, it should be an at, shouldn't it? There we go. Should be an at. So I've defined f of x here, and I apply that here. Ah, looks like Mathematica had a little bit of a wobbly. So I apply f of x, I define f of x here as being x squared plus 1, and now I've defined this function f, which is expecting some single argument x. I can replace that argument with a slot into which I can put in a set of values. And sorry, it's this notation that allows me to put in each of those numbers in turn into that slot. And notice that this notation is quite powerful. I can copy that and I can paste it in. And I can mix. I can put in v, I can put in 3c squared plus 2, and I can put in 95 if I like. And it will substitute whatever's in each of the elements of that list and substitute it into this slot over here. And actually, I don't need to do it this way. I don't actually need to define a function. I can define what's called a pure function in the following way. Imagine I wanted to square a set of numbers. So one way I could do it is I could do 1, 2, 3, 4, 5, and I could square those numbers. And you can see that I get the answer 1, 4, 9, 16, and 25, because this square function is being applied element by element to the elements of the list. But imagine if I want to do something a bit more complicated, which was to square all those numbers and then add something to it. I could do it like this. I could add 2, but that might not be as clear as I want to say it. Another way to do that would be to do the following. I could, perhaps writing this in brackets, I could say hash squared plus 2, and then I wish to substitute in and map at the things that I want to do that expression on. Okay, so the equivalent of what we were doing above would be the following. I would change that number to a 1. So rather than defining a function which is x squared plus 1, I can define hash squared plus 1 and then simply substitute in the things that I want to apply that expression to. And you can see that now it gives me the same answer that I had before. So just to finish off, there's one thing I haven't mentioned yet, which of course is having multiple arguments. So let's define a function that has multiple arguments. I'm going to define a new function g, which is a function of x and now a function of y. And again, because I'm not sure if I've done anything to conflict with my definitions, I'm going to quit the kernel. So this is as if I was starting afresh with a new run of Mathematica, so you can ignore all these lines up here. I'm going to define a function of x and x and y, which is equal to cos of x times sine of y. And notice that I don't need to enter the times value here in order for that to be okay. And there we go. And I now type g of pi comma 0, and this is 0. And if I now calculate 0 comma pi by 2, it's 1. Now, of course, I may wish to plot. Let's try plot. There's a plot 3D command. I'll plot 3D. Let's do a help on that. I'll do a query plot 3D. And yes, we wish to plot this function. So I'm going to plot g. And now I've got two sets of range that I can use. So I'll plot 3D, and I'll plot g of, and I'll call that, just to make it explicit that I can do this, I'll do L comma M. So wherever the values of L and M appear here, they will be substituted in for the values x and y here. And now I let L run from 0 to, say, 4 pi. And you can see that I don't need to put the times sign in again. And I'll copy that, and I'll put in the other set of parameters, which is M, and let that run again. And I hit return. And there is my function, which is a very convenient way of doing things. And I can rotate it is rather nice. And that shows some of the basic features of using functions. So I've defined a function with 2 arguments, and I've used that function where I've replaced the arguments with some other variables, and I can let those variables vary in some kind of multi-parameter function, such as plot 3D.